Yeah, good morning to one and all. Once again, welcome to the another session of the structure analysis. In this session, I am going to discuss about the analysis of the continuous beam using three equation of three moment, that is Clapeyron's theorem, that is discovered by Clapeyron's. So that is where the name has come as a Clapeyron's theorem. Otherwise, the another name is equation of three moments. The method itself is giving a very good information that what is meant by equation of three moments. So the equation of three moments is so we are going to use the three moment equation, that is where the three moment equation has come. But when you look at this numerical, which is able to see in this document, which is continuous but at the both ends having a simply supported, that is where the moment will be 0 at E CA by virtue of mechanics, and movement at C also will be 0, whereas B support is looking like a roller support, but still it is an internal support. So that is why the movement will not be 0 at the B. So a continuous beam ABC supports a uniform load Q. Determine the reactions, select RB as the redundant, then RA equals to RC equals to QL minus QL by 2. So force displacement relation equals to 5QL into 2L to the power of 4 by 384 EI equals to 5QL to the power of 4 by 24 EI. So RB into 2L cube by 48 EI equals to RB L cube by 6 EI. The compatibility equation will be followed actually. Then let us go with the another session. The whatever the discussion is being mentioned there. So that is continued here, and how to resolve that equations which is formed earlier with that expression by applying the three moment equation, and finally I could able to get that MA equals to P A square B by L square, that MB equals to P A square B by L square. Then under the reactions, minute. Okay, so this can be opened again, and the solving these equations we obtain which I have already told, and the reactions are RA equals to PB square by L cube into L plus 2A, whereas RB equals to PA square by L cube into L plus 2B. The deflection D can be expressed as D equals to D1 minus D2 D3, and D1 equals to PA square B square by 3 EIL 3L by EI, then D2 MA AB by 6L EI, that is into L plus B equals to PA square B cube by 3L cube EI, and MB AB divided by 6L EI, and P A cube B square by 6L cube EI, and P A cube B cube by 3L cube A equals to B equals to L by 2. Then the equation MA equals to MB equals to PL by 8, RA equals to RB equals to P by 2. Similarly, a fixed end beam AB supports a uniform load Q acting over part of the span. Determine the reaction of the beam. To obtain the moments caused by Q dx, replace P to Q dx A to x and B to L minus x, and dMA equals to Qx L minus x square by L square into dx, and dMB equals to Q x square L minus x into dx by L square. Then integrating over the loaded part, MA equals to integration of dMA equals to Q into the integration range is Q by L square of course, and integration range is A to 0 to A into x L minus x square into dx, and that is subjected to q square by 12l square into 6l square minus 8al plus 3a square. mb equals to integration of d mb equals to in q by l square integration of 0 to a x square l minus x into dx equals to, and finally after integrating everything you will be getting the values ma into mb equals to ql square by 12 and ra equals to rb into ql by 2. So the center deflection deflections due to uniform load and the end moments are like this. So now let us move on to the another document, that is the, of course what I told you, the three moment equation can be seen in an elaborated way here. The derivation of three moment equation for analysis of continuous beam can be seen here. Three moment equation means what? The continuous beams are very common in the structural design and it is necessary to develop simplified force method known as three moment equation for their analysis. This equation is a relationship that exists between the moments at 3 points in continuous beam. The points are considered as three supports of the intermediate beams. Consider 3 points on the beam marked as 1, 2 and 3 as shown in figure. Let the bending moment at these points is m1, m2 and the corresponding vertical displacement of these points are delta 1, delta 2 and delta 3 respectively. Let and L2 be the distance between points 1, 2 and 2 to 3 respectively. And the continuity of deflected shape of the beam at point 2 gives like this, and that is the expression actually. Then the beam can be seen here, one continuous beam having overhang here, and how to make the free body diagram also can be seen, and how to calculate that x bar, the centroidal distances, and m1, m2, m3 can be seen here, and the same thing will be followed what I have shown in the previous document. And using the bending moment diagram shown in figure and the second moment area theorem, where A1 and A2 are the areas of the bending moment diagrams of the span 1, 2 and 2, 3, and theta 21 is equals to 1 by L1 into 1 by E1 1 into m1 L1 square by 6 plus m2 L1 square by 3 plus A1 x bar 1, and theta 23 equals to 1 by L2 into 1 by EI2 m3 L1 square by 6 plus m2 L1 square by 3 plus A2 x bar 2 m1 into L1 by L1 by I1 plus 2 m2 into L1 by I1 plus L2 by I2 m3 into L2 by I2 equals to minus 6A1 x bar 1 I1 L1 minus 6A2 x bar 2 by I2 L2 plus 6E delta 2 minus delta 1 by L1 plus delta 2 minus delta 3 by L2. The above is known as three moment equation. The sign conventions are M3 are positive for sagging moment and negative for hanging moment. Similarly, areas and are the positive if it is sagging moment and negative are hanging. The displacements and are positive if measured downward from the reference axis. M1 minus M1 comma M2 and A1 comma A2 and A3 and delta 1 comma delta 2 delta 3. And example, if you see here, analyze the continuous beam shown in figure by the three moment equation. Draw the shear force and bending moment diagram. You can see here the problem is being given having the ABC span. In the ABC span there will be a central load that is 120 kilonewton is being given. So of course this problem I will continue in the next class and I will discuss in the next class. As of now I explained the typical procedure of the method.